Hey everyone, welcome to another of our HSC revision lectures. This time we'll be looking at ideas to implementation, the final core topic. We've already released videos on space and motors and generators, and I'll be releasing another video about study tips specific to physics and ways to approach your exam paper. Remember that whilst this video will go through a lot of the content in ideas to implementation, we can't go through everything, so always ask your questions on atarnotes.com. And you can also purchase complete course notes at atarnotes.com, which go through all of this content and more in much more detail. So we start off with cathode ray tubes. It's really important to understand the fundamentals, what a cathode ray tube is. We've got a cathode and an anode in a vacuum tube, which is evacuated of all gas and oxygen. Typically, this is going to have to be connected up to some sort of battery, so that the cathode can actually be charged up and cause a cathode ray to be produced. Now, Faraday was the first one to investigate these cathode ray tubes. Having discovered this crazy cathode ray phenomena, some experiments were done. Firstly, there's the Maltese cross experiment, where effectively a Maltese cross was placed in the path of the cathode ray, and a fluorescent paint was put on the other side of the Maltese cross, and it was observed that there was a shadow that was formed. Next, the magnetic field experiments. Now, initially, when these magnetic field experiments were done on the cathode rays, they showed no result. There was no clear movement up or down. That being said, when you do the experiments using modern technology, it's very clear that when you put a magnetic field in, the cathode ray, which we now know to be a beam of electrons, move in the direction consistent with a beam of negatively charged particles. Finally, the paddle wheel experiment was an experiment where they put a wheel on a hinge, a movable sort of track in the way of the cathode ray tube. The paddle wheel spun in the direction that the cathode ray was traveling. This suggested that the cathode ray had momentum because it caused a sort of pushing force on the paddle wheel, which then caused the paddle wheel to spin. Just to sort of summarize this, there was an argument as to whether the cathode ray was a particle or a wave. The Germans were arguing that it was a wave. Typically, when the Germans argue something against the British, the Germans tend to be wrong. And so in this case, they were. Germans claimed that the cathodes were waves because they traveled in straight lines, they produced shadows, they could pass through thin metals, and they fluoresced phosphors. The British, on the other hand, claimed that they were particles. They were emitted perpendicular to the cathode, they didn't radiate. They seemed to have momentum and thus mass. They traveled much, much slower than light. And eventually J.J. Thomson came along and resolved the argument. He found that the particles had a charge to mass ratio, and if they had a charge to mass ratio, they definitely had a mass, which meant that they were particles. Cathode rays were used in old television sets. You probably had one as a kid. Usually you have three distinct cathode rays, red, green, and blue. They experience deflection in the X and Y direction using magnetic field plates or electric field plates. And the screen was covered by the three cathode rays 60 times per second. It just scanned across with different combinations of light, which created a picture. You can imagine that when the TVs go fuzzy, there's sort of lines that go across the screen. That's because the cathode ray isn't properly aligned, or the proper signal isn't being fed into the cathode ray, something like that. Great, so now we move on to the photoelectric effect. And we look at the Hertz experiment. So initially, Hertz was looking at sparks and how sparks work and where sparks came from. He had an induction coil, and there was a bit of a gap between the two ends of the wires. And he found that if you put lots of current in, eventually there was a spark between the two wires. Nothing too interesting there. What was interesting was that on the other side of the room, whenever there was a spark in the I guess used equipment, the equipment that wasn't being used on the other side of the room would occasionally spark as well, despite having no current input into it. He found that there was less sparking in the receiver in low light conditions, but basically Hertz said, look, this isn't my thing, I don't really care, I'm not going to investigate this. But this turned out to be the first, I guess, observing of the photoelectric effect. In terms of the investigation, we have to introduce a concept called black bodies. Now, black bodies is a complex idea that's definitely glossed over in the HSC course. There's no need to understand it to any depth beyond that it's some sort of object that will absorb all wavelengths of radiation and re-emit the same wavelengths of radiation. Now, they simulated this, they did some experiments on black bodies. They classically expected the black curve in the bottom left, but instead they found curves similar to the colored curves on the same graph. And this was known as the ultraviolet catastrophe of 1911. Effectively, it said, well, what we thought of in classical physics can't be true, not just because we didn't find it to be true experimentally, but also because the classical theory violated conservation of energy principles. So Planck, like any good physicist, makes something up. They have no idea how to solve this problem, so Planck comes along and says, you know what, the maths just kind of works out. If we pretend that light isn't a wave, but rather light is a particle, we'll call the particles quanta, and they come in packets. He said that the greater that the intensity of the light that is input will not result in a greater release from the black body or from any objects. It's all about the frequency of the light. He also created the formula E equals HF, or at least posited the formula E equals HF, where E is energy, F is frequency, and H is the Planck constant. Einstein in 1905 releases his paper on the photoelectric effect, in which he goes a bit further. He says that light does consist of photons, and that's not just mathematically true, that's physically true. He says that photons can give up all or none of their energy to electrons that they are incident upon. The electrons can jump off the metal, where the photon kinetic energy is converted to the electron kinetic energy, if the electrons are being bound by energy that's less than the energy given to it by the photon. Higher intensity of light just means more photons of the same energy, because E equals HF. Once all of the photons have jumped off, the intensity won't affect the discharge because the electrons are too attracted to, for instance, the nucleus of the particular metal. You need a higher energy light to bounce those electrons off, and higher energy means higher frequency, not higher intensity. These are curves you'll be really, really familiar with by now. This is the E equals HF curve with a work function. So it's E equals HF minus phi minus the work function. And clearly it's not dependent on the intensity of the light, it's dependent on the frequency. In terms of uses, it's used in photography, measuring equipment, sliding doors. You can imagine that wherever light is incident on a cathode, it can expel electrons by the photoelectric effect towards the anode. If you place something in the way of the incident light, then all of a sudden the circuit stops working, and so maybe a door opens or something like that. Just to summarize, the photoelectric effect, and Einstein in particular, suggest that light comes in packets that can only eject electrons if photons are equal to or higher than the energy of the electron. Increasing the frequency will eject more electrons, and increasing intensity will eject more electrons, but only electrons at that same energy. So you'll increase the voltage, the photo voltage, but eventually those electrons will effectively run out, and you'll need to input a higher frequency light in order to continue the current. We're just going to quickly look at an extended response question, and particularly the methodology that I recommend using when approaching extended response questions. I'll be creating an entire video on this, so basically just have a look at the information at the bottom, think about it, think about that structure, but keep an eye out for a future video where we go through it in more depth. So the question is a very common one. It says Einstein's contribution to quantum theory. First, I'd be thinking about what the question is actually asking. It's a contribution to quantum theory. So perhaps you'd be thinking about what was quantum theory before Einstein's contribution? What was quantum theory like after Einstein's contribution? How did he change it? In terms of structure, you'd talk about Planck's hypothesis, Einstein's postulates, and it is an assess question. So you have to find some way to assess the impact of the contribution. And that's a tough one, but we'll have a look at how we might think about doing that a bit later on. Then think about the particular specific information that you can use to really make your answer stand out. You'll definitely want to use words like ultraviolet catastrophe, Planck's postulates, Einstein's explanation, perhaps the result of Einstein's contribution. Again, we'll have a look at that in a bit, but I think that that really makes an answer to this question stand out because it is an assess question, so you have to come to some sort of judgment. Finally, you want to think about the diagrams and equations that you can use. In particular, you can use the ultraviolet catastrophe graph. That's the black body radiation curves, the classical curve, and then the quantum theory curve. Additionally, you can talk about maybe like what the results of understanding the photoelectric effect, what the new graph looked like, maybe some new technologies that were developed. Now, here's an example answer to this question. I just want you to have a quick read through it. I've put the colors in myself. Pause the video, take a read through, see what you think. This is a answer given by the Board of Studies. It's on the Board of Studies website. I would suggest that it's not very good. The red is the thesis, the actual answer to the question. The green are the specifics. E equals HF should also be in green, but everything else is not really particularly useful. I would say that you need to be packing a lot more into your sentences, a lot more specific detail, a lot more of an answer to the question, because you just don't have time in a physics exam to be writing stuff that's not relevant, and markers will lose interest if your answer is too long. Things you'd be wanting to think about is that, like, what were Einstein's contributions? Well, there was the all or nothing principle, the photons, the explanation of the photoelectric effect. This is just a very brief summary. Obviously, this is not a complete answer. However, in terms of the assessment, personally, I would think about what the understanding led to. For instance, solar cells, application of the quantum theory to many technologies, the wave-particle duality of light. These contributions are all measurably positive. And so you could say that his contribution led to these technologies and that therefore is a good thing. It's up to you how you want to play that, but that's just how I would deal with a weird assess question. Now let's quickly move to semiconductors. We know that in metals, the valence electrons form a sea of delocalized electrons that aren't like tied to a specific atom. They just float around generally. This is why metals conduct. It's because it's easy for current electrons to flow across the top of the atoms. Now we've got three types of materials that we're interested in: conductors, semiconductors, and insulators. It's really important that you're comfortable with the band notation by now. In a conductor, the conduction and the valence band are touching. In a semiconductor, they're not quite touching. In an insulator, they're further apart. I would recommend finding information about how far apart these typically are. I think semiconductors are about 1 electron volt or something like that. Having values like that is really the way to get great marks. I mean, the reason I got a band 6 was because I had a lot of detail that I could include in every long response answer that really makes the difference between a 4 out of 6 and a 6 out of 6. Here's an example of a question that I think throws a lot of students because it's not super easy, it's not obvious. So let's have a quick look. Which material would absorb a photon of wavelength 8.6 times 10 to the minus 7 meters, causing an electron to just jump the band gap? Okay. So first of all, we know that E equals HF. That's just the formula we've got. So we plug in E equals HF, but we don't have frequency. We have wavelength. Again, we need to remember that velocity is frequency times wavelength, as on our formula sheet. So we sub in frequency for velocity divided by wavelength, put all those numbers in, and we get that the energy of the photon that we're interested in is 2.3 times 10 to the minus 19 joules. Now, this is in joules and we need it in electron volts. So we go to our formula sheet, which tells us what an electron volt is in terms of joules. In this case, we divide by the value of the electron volt, which is 1.6 times 10 to the minus 19, the charge on the electron, and we get 1.4 electron volts. So obviously the answer here is going to be C. The interesting part of this question is you could have never seen it before, you could not have any idea how to do it, but based on your formula sheet, there's only one possible way to get to an answer. Again, if you've ever got a question that you can't do, a maths question, just go, don't think about it, write down the relevant information, go to your formula sheet and just see what you can do. I'll have a whole video on dealing with maths questions and extended response questions, so keep an eye out for that. So how do semiconductors actually work? We haven't talked really about semiconductors at all yet. Well, metals such as gallium and silicon are semiconductors. They have 4 valence electrons. However, we want to make them conduct even better, so we dope them. There are 2 types of doping. There's p-type doping, in which we add group 3 metals like boron and aluminium. This leaves a hole, a lack of an electron somewhere, which you can think of as genuinely a positively charged hole because it's not the negatively charged electrons around it. the electrons sort of jump into this hole, and the next one jumps into the hole left by the first electron, and da-da-da-da-da, until you can think of it as a current moving in the direction that the hole originally was. N-type doping is where we add a group 5 metal, arsenic, phosphorus. An extra electron is added, which is more easily transmitted across the top of the surface. It goes to the valence band, it's free to move, and the moving electrons are the definition of charge. Here are just some examples. We can see that the bottom left is an N-type, there's an extra electron. The bottom right is a P-type, there's a hole. Now, it's really, really important that you know the answer to this question. This question gets asked fairly regularly, and there's no way to figure it out. This is just one of the blatantly memorizing points. So here's the answer. It's D. You need to know that for P-type, it creates an acceptor level above the valence band. For N-type, it creates a donor level below the conduction band. Not much more to say about this. It's important that you include that in any extended response answer, not because it necessarily means anything, but because it's what the markers are expecting. Looking at transistors now, a lot of students, when they're over preparing for the HSC, learn like how transistors work and what they are and what they do. The HSC doesn't require you to know that. I personally definitely spent way too much time learning what a transistor was, and it cannot be assessed. It cannot be assessed. What you do need to know is that it was developed during World War II to replace the bulky, fragile communication equipment known as thermionic devices, which we'll talk about in a second. You can know that there are NPN or a PNP junction. And if you really wanted to know some like, let's sound like I know what a transistor is, you might want to throw the words depletion zone in. Basically, transistors create a depletion zone which allows the transmitting or stopping of current, blah, 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 blah. Nothing important, definitely nothing that you need to know. What you do need to know is the comparison between transistors and thermionic devices. The top right is a thermionic device. The great thing about this comparison is that transistors are better in just every possible way. So if you can think of a way, cost efficiency, weight, warm-up time, size, transistors are better. Here's my list. Learn it, memorize it, understand it, be ready to answer questions using it. Okay, outline some advantages and disadvantages of the invention of transistors on society and the environment. Here is a potential solution to this question. I would have actually structured this in a table rather than in dot points, but dot points like this are fine as well. The advantages include global communication, widespread use of technology, increasing knowledge. Environmental advantages are that transistors are very durable, so unlike thermionic devices, they're not breaking all the time, which means that we don't need to replace them all the time. Now, the disadvantages are always pretty typical. You can come up with real ones, or you can come up with fake ones. So the fake ones include things like, I don't know, transistors created a dependence on technology, which reduced personal communication skills. I mean, like, personally, I think that's rubbish, but it is technically a disadvantage, and it's one that they are looking out for. You can also say that because the devices don't break as much, it requires fewer jobs to produce, which would have lost people jobs at the time of transistors being developed. Again, I would say it's a stupid disadvantage, but it is a disadvantage all the same, and you have to include disadvantages. Environmentally, the disadvantage would be that now that we can produce such small transistors, hundreds of millions of them are produced, which requires burning of fossil fuels to produce and also increases landfill because of how many mobile phones and computers we've got nowadays. And finally, an application of semiconductors are solar cells. You've got sunlight incident on the solar panel. There's an N-type semiconductor at the top and a P-type semiconductor at the bottom, as you can see by the little blown up chart in the bottom left. The photoelectric effect means that the incident photon bumps off an electron in the valence band. It travels around the circuit, lighting up the light bulb, hits the P-type semiconductor that's at the bottom of the solar cell, which has a hole. So the electron can jump into the hole and move up the P-type semiconductor until it again reaches the N-type semiconductor. Sorry, I'm confused, but the diagram in the bottom makes it really clear. Which means that the electron can then be bounced off by the photoelectric effect again and again and again and again. Okay, let's look at superconductors. I know that we're going a bit over time, but that's okay. It's a pretty long topic area. Recall that metals have a sea of delocalized electrons. We've just talked about that. In metals, impurities impede electron flow. So if you've got little extra atoms, little impurities. As the electrons are flowing through, they bump into the impurities and slow down. Additionally, when you increase the heat of the metal, the ions and the lattice itself is vibrating a lot, which means that electrons bump into the vibrating lattice and they slow down. So increased heat increases resistivity and decreases the current flow. In terms of superconductors, though, when temperatures decrease, usually you'd expect a decrease in resistance. But superconductors experience no resistance under a certain critical temperature, as you can see by the graph at the bottom. This is explained in the HSC through the BCS theory. Now, the BCS theory seems complicated, but actually I would probably memorize exactly what I've got written on the page here, and then you'll probably get full marks. I'd also probably draw a diagram like I've got in the bottom right. So when lattice vibration, when the temperature is 0, the lattice vibration isn't quite 0. It says here that the lattice vibration is 0 because it effectively is, but there will still be a little bit of vibration. So we wouldn't expect there to be no resistance, but for some reason there is. The electrons, being negatively charged particles, cause the positively charged lattice to bend towards them. That makes sense. You can see that in the bottom right diagram. This creates an area of positive charge. And that also makes sense. There's a higher density positive charged region. This is where it gets a bit crazy. By quantum theory, this creates a phonon. A phonon is just a particle of vibrational energy. The electron then forms a Cooper pair, which is with any other electron at any point in the lattice. The phonon created by electron 1 is transmitted to electron 2, which causes electron 2 to speed up. These Cooper pairs constantly form and break. It's not necessarily the closest electron between which the Cooper pairs are formed. Now that's weird. The part about the phonon, the part about transmitting the phonon and speeding it up, that doesn't really make a whole lot of sense because we don't know a whole lot of quantum theory, but that doesn't matter. Just be able to say it, understand it, and write it down. Reiser Effect, effectively because superconductors expel magnetic field at when they're below their critical temperature. Whenever you put a magnet above it, it will just float. The magnetic field downwards will be repelled by the field causing the eddy currents that are being formed on the surface of the superconductor. By Lenz's law, any change in direction, so if the magnet moves one way, then the field will oppose it and try and make it move the other way. So eventually the magnet just stays still. Schools learn this in many, many different ways, so I'm not going to go in depth here because I don't want to confuse anyone. In terms of maglev trains, the maglev trains don't actually use the Reiser effect. Not sure why it's under this dot point. We use electromagnets and permanent magnets built into the base of the train and the tracks, which obviously repel each other. Superconductors are used because they are cheaper than electromagnets and have the same field strength. So we do use superconductors, but just because they're great. We love superconductors. Finally, we look at the uses of superconductors. No heat is produced in the transmission of current, so we don't need to cool the superconductors down once they're at their critical temperature. We can produce smaller microchips because of this, and potentially we can use quantum computing through the use of superconductors. In motors and generators, we can increase the efficiency because there's no lossage due to heat, and this means that it yields more energy per unit. In terms of power distribution, again, there's no resistance, so it's 100% efficient. We can use thinner wires, which are more environmentally friendly. This will only transmit DC current. At the moment, we use AC current across long distances, so we'd have to change our structure of electric generation. And it also requires a coolant, because obviously it needs to be below the critical temperature. A huge area of research is creating superconductors that superconduct at room temperature. If you do that, you'll probably win a Nobel Prize. Billions of dollars, and feel free to cite me for the idea. So yeah, that's about it. That's the end of our ideas to implementation video. Hopefully you've learned something. It's been a bit of a longer video, but it is a much more conceptually difficult topic. As always, if you've got any questions, jump onto atarnotes.com and ask them. They're totally free. If you need a further explanation on anything that we've listened to, we sell $25 course notes on the website at atarnotes.com. which are complete course notes that go through all 3 core topics. I'll be releasing another video on study techniques and exam techniques for physics, and we've also got a huge number of videos for a huge number of subjects. So keep an eye out for all of those. Good luck for your physics exams, and thank you.